Hey guys, today we're going to look at 5.4, which is going to talk about logarithmic functions or logarithms. Now, a logarithm is the inverse of an exponential function. So exponentials, you've got a base and you're taking it to different powers. Okay, a logarithm it's the opposite of that. It's the inverse of that. So this is an example of a logarithm. Okay, y equals log base a of x. Okay, so just like exponentials, we have a base. That's what that number right there is. And the connection between logarithms and exponentials is this statement is true, y equals the log base a of x, if and only if a, our base, to this power equals this value right here. So if a to the y power equals x, so notice they took the x and the y and they flipped them because that's what inverses do. Okay, so a to the y power equals x. If this is true, then y, which is an exponent, that's with logarithms, that's what your answer is. Your answer is an exponent. You're trying to find what is the exponent that I raise this base to get this value right here. Okay, so if you need to reread this a couple times until it kind of makes sense, this is how you say this: y equals the log base a of x. But understanding what it means, y is the exponent that you would raise a to get an answer of x. So when you see log base a of x, it's literally saying what exponent would you raise this to get this. Okay, and we're going to do some examples with that to hopefully make a little bit more sense. I will tell you, logarithms are not intuitive. Okay, when you learn how to do 2 times 3, because it's a 2 and a 2 and a 2, and you can add those together and get 6, you can kind of intuitively understand what multiplication means. With logarithms, you're going to have to kind of stop and think about it. Okay, and you're going to have to stop, say it in your head. Okay, what power do I raise this to get this? And then you're going to have to think about it. Okay, so don't worry if it doesn't just click. Okay, some of these you've got to kind of think about. Now, the domain and range. Now, remember, logarithms it's the inverse of exponentials. So with exponentials, our domain was all real numbers. So our range will be all real numbers. And with exponentials, your range was always y values that were greater than 0. So our domain will be x values that are greater than 0. So we're only going to get positive answers when we're doing logarithms. We're not going to get negatives. Also, this base right here is never going to be a negative. Okay, so the base is always going to be something greater than 0. It's also not going to be a 1. And that's what that base is. Okay, so again, if you look at a problem like this and it says log base 2 of 8, the answer to that is 3. Why? Because this is saying what exponent, what power would you raise a 2 to get 8 as an answer? Okay, and the answer would be 3. 2 to the third power equals 8. And that's what a logarithm is. So I've got some examples here where I just want us to kind of think through what these are. So what is the log base 4 of 64? What power would you raise a 4 to get 64 as an answer? So 4 times 4 is 16, times another 4, that'll give us our 64. So the answer is 3. The log base 4 of 64 is 3. What is the log base 5 of 1? It's 0. Why? Because 5 to the 0 power, anything to the 0 power, equals 1. What about the log base 2 of 1/8? Okay, what exponent would you raise 2 to what power, to get 1/8 as an answer? Well, there is a connection between 2 and 8. 2 cubed is 8. So if I want 1/8 instead of 8, it's going to be -3. That is the exponent that I would raise 2 to get 1/8. Now, every time I do these, I'm kind of rewriting the logarithm as an exponential. And that's something you need to learn how to do. You can rewrite logarithms as exponentials. You can rewrite exponentials as logarithms. So what I'm doing in my head is, so this is an equation, y equals log base 2 of 21. As an exponential, it would be 2 to this power equals this answer. 2, which is my base, to the y power equals 21. That's it. That's all you need to be able to do. For example B, this base to this exponent. That's what that is. That's an exponent. So z to the 6th power equals 12. That's it. That's all we're doing. For example C, 2 to the a equals 10. And you can write that as 10 equals 2 to the a power. So the direction that you're writing this doesn't matter, but this base to that power, that does matter. Okay? So what about going backwards? What about going from an exponential to a logarithm? Okay, so again, log base, well, your base is that 5 right there. That's the base of the exponential, and that's going to be the base of our logarithm. So log base 5 of t equals 8. Now, I will be honest with you, that's actually not how I normally start these. When I have an exponential, I usually just write down the exponent first. Okay, because that's the thing that goes over here all by itself. So for this, if I write down, so I'm rewriting this as a logarithm. So -2 equals, and it's going to be the log base, what my base is. So this has a base of x. This will be a base of x. And then you just write down the number you haven't used yet, 12. For the last one, x equals log base 2 of 10. Okay, so that's writing logarithms as exponentials and exponentials as logarithms. You need to be able to go back and forth. Now there's 2 logarithms that are so common that they kind of get their own notation. And you're going to see these buttons on your calculator. Log base e and log base 10. Sorry, I was making another video earlier and it started playing. All right, so these 2 are so common they get their own notation. Log base e is the natural number, and it's called a natural logarithm. If you look on your calculator, you'll see an ln button. An ln, which is, it's French, it's logarithmic natural. That's why it's in that order, even though we call it a natural logarithm. Okay, it is a base e. Okay, so whenever you see natural log, it is a base e. They are not going to write that e there. That's just understood. If you want to write it, just so you see it and you're more comfortable with it, that is fine. But y equals the natural log of x if and only if e to the y power equals that x value right there. So x equals e to the y power. Common logarithm, that's base 10. Okay, so 10 to what power equals some value. So 10 is our base system for our numbers. So that is called the common logarithm. Again, you will not see anything written here. You're just going to see the word log, log of x. It's log base 10 of x. So 10 to the y power equals x. That's the exponential that this is equal to. Okay, so when you're asked to rewrite something as a logarithm or as an exponential, okay, again, this is a base 10. They just don't write the 10. So it's 10, and if you want to put it there, that's fine. 10 to the x power equals 52. 10 to the x equals 52. Okay, natural log of x equals 6 means e to the 6th power equals x. Going the other direction, this is a base 10, so we're going to write it as a base 10. X equals log base 10, we don't have to write it, of 180. And that's something you could do in your calculator. You actually have a button on your calculator that says both log and ln, natural log. Okay, we're going to use those in a second. And then this last one would be x equals the natural log of 9. Okay, so that's how you write them. So how would you approximate these using your calculator? And these are the only buttons you have on your calculator. You've got a log base 10 and a log base, or a natural log. Okay, so this right here, what is the log of 20? So what it means is 10 to what power equals 20? Well, 10 to the first is 10. 10 to the second is already 100, so it's going to be some decimal that's between them. So if you take your calculator and just hit log 20, okay, I got 1.301. So 1.301. So watch this. 10 to the power, and then I'm going to hit my answer button, and that's going to record the last answer I just did. So I'm taking 10 to the 1.301 power, and I'm going to get 20 as an answer. Okay, so that's the exponent that I would raise the number 10 to get 20 as an answer. For B, what's the natural log of 5? Now this one we're going to have a hard time thinking through because natural log is that E. So that's 2.7. What is the exponent that we're going to raise 2.718 to get 5 as an answer? But we don't have to do that. We're just plugging it in our calculator. Natural log of 5, 1.609. Looks good to me. 1.609. Okay? Now, this last one, I want to see what is the log. So this is a huge expression that we're going to try to find. There are two ways to do this. You can do it all at once. It takes a lot of parentheses to do all of this in one step. What I normally say is to simplify the top. So just figure out what the log of 10 plus the log of 15 is. So log of 10, close your parentheses. Okay, you'll notice that there was a parenthesis there, so I need to close it. Plus the log of 15, close it, and then get that answer. So 2.176, we'll say 2.176, we'll say 09. Divided by, and then you do the bottom. Natural log of 10, close your parentheses, plus the natural log of 15, close your parentheses, and 5 point, so what do I got here? 5.01064. 064. And then divide those two numbers. So now take the 2.17609, divide it by, now this one I could use my answer button. It'll record that last answer we had. And we'll get 0.434. That'll be good enough for us. Okay? So if you want, you could try to do that all in one step. The problem is this number is going to have parentheses around it. This number will have parentheses around it. But you also have to tell your calculator that all of this is connected. So you have to start and end with parentheses as well. And then that'll happen on the bottom. So you'll start with parentheses. Then there'll be a parenthesis there and one there. There'll be one there and one there. And then you'll finally close. So that is what you would type into your calculator if you want to do this all at once. And if you want, pause it, try it, and see if you can get that as an answer. Okay? So the last thing we're going to do is we're going to graph logarithms. Now, we've got two examples right here. This is an example. So first, look at the exponential. This is an example of exponential decay. And then this is the logarithm that would be the inverse of that. This one's a little bit easier to read. Okay, this is exponential growth. And we said that a logarithm is the inverse of an exponential. And so you can see, here's that line, y equals x, and you can see that this graph is symmetric across that line. Remember, our exponential has points 0, 1, 1a, so you go over 1, you go up whatever the base is. You go left 1, you go up the reciprocal of the base. That's our 3 points that we graph on the parent graph of an exponential. So the logarithm is going to have those flipped. Okay, so you're going to have the point 1, 0. You're going to have the base 1, and then you're going to have the reciprocal of the base, which is normally going to be a fraction in this case, and then negative 1. Remember, for an exponential, the x-axis was a horizontal asymptote. So for a logarithm, the y-axis will be a vertical asymptote. So this graph is going to curve down, 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 down towards infinity. This is the logarithm when you have a base that's like a whole number, like a number, not a fraction, a number greater than 1. This is what you're normally going to see with logarithms. over here, this is exponential decay, and this is the logarithm that is the inverse of that. It's a little harder to read, but it is something that can come up, and you can always do a t-chart to figure out what exactly that graph looks like. But again, if we focus over here, we can see some properties. So like the domain, it's all the x's greater than 0, which we said on the front page. The range is all real numbers. This goes to infinity and positive infinity, so all real numbers. This one has an x-intercept. Okay, the x-intercept is 1, 0. There is no y-intercept because the y-axis, so the y-axis is a vertical asymptote, so the y-axis. Now, this graph will always contain the same 3 points. Again, we're going to talk about them generically using the letter A as a base, but they will always have the point 1, 0. They'll always have A1. And then there will always have 1 over A, negative 1. So, you don't have to memorize those 3. Those are the exact same points we did for the exponential. Okay, so anything to the 0 power is 1. Anything to the first power is itself. You just have to remember those, and then the logarithms are those 3 flipped. Okay? So, when I come down here and I say we're going to graph the parent graph using these points, but then we're going to use any transformations and shifting that the problem tells us to do. So like this one, 2 times log of x plus 2. So first off, make sure you understand what your base is, your A. Okay, this is a base 10. Okay, so that's our A. So our starting points are going to be 1, 0. It's going to be 10, 1. And it's going to be 1/10, negative 1. That's our starting points. Okay, now how should we translate? Well, the plus 2 that's inside with the x is going to tell us to go left 2. So we're going to go left 2. And then this 2 right here, that's going to be a vertical stretch. So we're going to stretch by 2. So again, what I'm going to do is I'm going to start with these 3 points. I'm going to graph them. I'm going to graph 1, 0, 10, 1, and then 1/10, so we're going to approximate that, over 1/10 and down 1. Okay, so these 3 points, if I do a dotted line, this would be our logarithm. This is the graph of our logarithm. Okay, but now I have to do what they've told me to do. I need to go left 2, so I'm going to start on the middle. I'm going to go left 2, and then stretch. Well, if you're sitting on the x-axis and you stretch vertically, you're still sitting on the x-axis. Your y value is 0, so it's not going to get stretched. So that one's going to kind of stay centered. This point that was over 10, up 1, we're going to go left 2. And then instead of up 1, we're going to be up 2. That's going to be our stretch. So we're up here now. And this point is going to be left 2. So now we're 1/10 away from negative 2. But we're also going to get stretched, pulled down. So we're going to be right here. Now, we had a vertical asymptote at 0. So now we're going to have a vertical asymptote over here at negative 2. And that's the line we're going to follow. Our graph's going to go up, 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 curve. And then it's going to go through that point. And that is the graph of our logarithm. Okay? The domain of this would now be all x's greater than negative 2. The range is still all real numbers. And we have a vertical asymptote. The reason our domain is what it is because we have a vertical asymptote at negative 2. Okay? Well, look at B. B, that's a natural logarithm. So this is a base E. So we want to start with our parent graph points. That's going to be the point 1, 0. It's going to be our base 1. Well, the base E is 2.7, comma 1. And then the reciprocal of our base, which is 0.37, negative 1. So that's what we're going to start with. We're going to graph those 3 points. 1, 0, 2.7 up 1, and then 0.37 down 1. We're going to get a graph that looks like this. This is our exponential. Okay? Now we're going to look at our transformation. The x minus 1, that means go right 1. And then the 3 is going to be, we're going to be stretching this graph by 3. So anything that's above the y-axis is going to get pulled up, or the x-axis is going to get pulled up. Anything below the x-axis is going to get pulled down. Okay, so stretch by 3. All right, so we're going to go right 1 and stretch. So I'm going to take this point, go right 1, and then it's going to stay put. This point is going to go right 1, and it's going to get up. Now, I'm going to go up 2. Why did I go up 2? Well, I was already at 1. I'm stretching it by 3, so it needs to go up to 3. So that's what this is right here. Okay, so I stretched it up. This point, I'm going to go right 1, but I'm going to pull it down. So instead of down 1, it's going to go down 3. I'm also going to take this vertical asymptote, shift it over 1, so I can use it as a guide, and then my graph's going to go up, 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 and then curve and go that way. Okay, so that is the graph of 3 natural log of x minus 1. Okay, and you can plug that into a graphing calculator and it would do that, but we can do it just by following the stretches and the shifts and things like that. Your domain would be all x's greater than 1 because we have a vertical asymptote at x equals 1. And again, our range is all real numbers. So take a look at the skills practice worksheet and try those on your own. All right, thanks.